In this video, I'm going to discuss polarization. It is part of topic 4.3, which is in the IB Physics Syllabus in the SL section. Please take a moment to read the success criteria that we will use for this video. Here's the equation for Malus's law that can be found in the data booklet. Okay, so first let's remind ourselves what EM waves look like. We have a oscillating electric field, and in this case I've got it drawn in red, and it's going in the vertical direction. When it oscillates up and down, this changing electric field is going to cause a changing magnetic field, and you can see that I've got that here in blue. And the magnetic field is actually perpendicular to the electric field. That's always going to be the case. A lot of the times in this section we just talk about the electric field because of the fact that we know the magnetic field is perpendicular. I could have been talking about the magnetic field all the time. It's just conventional that we typically talk about the electric field. Okay, so if you take a look, here's our electric field going up and down, but the actual propagation of the wave is in this direction. Now, if I was to look at, down this direction of the wave, if my light, and I was looking at it and it's just normal light given off from the sun or a light bulb, it would actually look like this picture right here. That electric field can be in any random direction as it's coming towards me. That's what we call unpolarized light. But if light's polarized, then somehow what I've done is I've made that electric field only happen in one direction. So if I was again looking down this arrow here, I would see all my electric fields. It could be vertically or any other direction, but the point is it would only have one direction possible. So how could I actually make that happen? Well, one of the ways is to use a polarizing filter. So here I've got my light coming in from, say, the sun or an incandescent light bulb, and my electric fields are in all possible directions. When it passes through this polarizing filter, what happens is, remember when we have light interacting with a medium, it could be reflected, absorbed, or transmitted. And so what happens with this polarizing filter is it will only transmit the light that has the electric field in this direction. Well, actually, it will, in this case here, it will allow the vertical component of this vector through as well. Now, because of that, because it's only letting through the vertical component, because that's the direction of my polarizing filter here, what happens is, of all the light that I have incident on my polarizing filter, only half of the intensity is going to get through. Now, if I have more than one of these polarizing sheets, I can do a lot of really cool things. So, for example, here's my unpolarized light, and it goes through my first polarizing sheet, and it only allows the vertical components of the electric field of the light to come through. If I put a second one, and we typically call that the analyzer through, if I put it at an angle, then it's now only going to allow the components that are parallel to this new polarization axis through. Now, if I have this second one here at 90 degrees, realize that this only has a vertical component, and that would mean this one here would only be letting through things that have a horizontal component of the light, and nothing will get through. So I can actually have multiple of these polarizers in a row. So take a look what I've got here. The first one is only going to let light with the electric fields or the components of the electric fields vertically. My second one's on an angle here, so it will let any components in this direction through. Now suppose I had a third one, and it was again in the horizontal direction. Remember I said on the last slide, if I had the first one vertical and the second one horizontal, nothing would get through. But that's not the case here, because now I have this first one vertical. The second one is on an angle, so it's letting components in this direction. If I have a third one that's now horizontal, realize that this angle here has a vertical and a horizontal component. So when it gets to my third polarizing film here, I actually will get light to come through. I've just put a link down at the bottom of the screen here. It's a link to a video by 60 Symbols. It's through the University of Nottingham, and it has a really good video of exactly what I was just showing here. But in addition, it has polarization where it uses microwaves rather than visible light. I think it's a really good extension, and polarization can happen with any of the EM spectrum, not just visible light. So please check it out. Okay, so I've already said that if I have unpolarized light that lands on a polarizing sheet and creates polarized light afterwards, I'm going to have an intensity of 1/2. And that's basically because it's removing all of the components of the vector that's going to be perpendicular to its polarizing axis. In other words, it only lets the vertical components through in this case, and it's going to remove the horizontal components. But the question now is, I have this light that's polarized and I have a second filter. And if it's on an angle, how much of the light actually gets sent through? Now, I'm not sure what's happened here with my subscripts, but this should read the intensity equals the original intensity cos squared phi, where the phi is the angle between them. Notice that if I have cos squared, we know that cos of 90 degrees is 0, so that means that no light or 0 intensity will make it through. This will be repeated again at 270 degrees. This is one of those equations, just like Snell's law or Faraday's law, that the equation itself actually has a name, so it's a good thing to recognize. Now, you may have seen polarized sunglasses, or even the 3D glasses when you go to the movies now are polarizing film. The polarizing ones for the 3D glasses, though, are not quite what I've been talking about. There's actually something called a rotational polarization, and this course is only talking about plane polarization. So in other words, it's keeping the electric field in one direction. But if you're interested in that, it's kind of cool to find out what happens with the light with the 3D glasses. So polarized sunglasses, though, are plane polarized lenses. So let's take a look at what we've got here. If I have light coming off the sun, as I've said before, that's unpolarized. And then if I have the light here and it's going to reflect off a surface, then it's actually going to be partially polarized. There happens to be one particular angle, though, at which all of the light will be polarized, and it's polarized in this fashion here, where the electric field is parallel to the surface. Now, when I have polarizing sunglasses, what happens then is I'm going to set them up so that the polarizing axis is going to be vertical here, which means I'm not going to get this reflected light. What does that do? It removes the glare from the top of the water. So I still see light coming from the water here, but I'm not going to get this reflected light. And what that does is means it's easier to see the fish, or in this case the shark, underneath the water. Sometimes you can also get this kind of polarizing film for your cameras as well. Now, you can calculate what that angle is going to be, and it's related to the difference in the index of refraction between the, in this case, air and water. And you could go and you could calculate it. It's actually called Brewster's angle. And notice the but. There usually is a but, and this is a big, big but. This is no longer on the syllabus. So if you see videos or you see textbooks or questions that ask you to calculate Brewster's angle, they are from a previous version of the syllabus. I just think it's good to know, and it's kind of interesting to find out what the whole reason for polarizing sunglasses really is. So that's just a quick walkthrough for polarization. I hope if you read these success criteria now, you can actually say, yes, I can.